fully fit the screen. Anyway, so if you've ever been writing programs with session types in a functional language, you will know that this is like a concurrent lambda calculus. You have communication primitives, and they're usually typed like here. So you have, let's say, the send primitive. It takes some data to send. Then the session type, the type of the channel you're sending on, says, on me, you can send an alpha, and then the communication continues according to sigma, and then the primitive returns the depleted channel of the let's call it continuation type sigma here. And as you can see here, the received primitive has like the same structure, only that now the prefix of the session type says receive an alpha, and then continue as sigma, and then of course from receiving you want to return what you received, and also the remaining continuation channel. Now this gives rise to a particular, oh, that's interesting. This gives rise to a particular style of program that we like to call resource passing style. Now suppose we have a longer session type with two communication actions, sending an integer, receiving a bool, and now we only want to perform a prefix of that calculation. All right, now you do that. After sending the first message, now you are left with, well, receive a bool and close the channel. But notice here, in the type, you have this kind of annoying repetition of this continuation. Well, people have invented polymorphism, maybe not for this, but now you can make this function more flexible by abstracting over the continuation. Yeah, so I say, for all sigma, I just want to send an integer, and then any kind of continuation protocol is okay with this function. Now consider what happens if you want to write some primitive that takes two channels and wants to do two prefixes of the protocols. So this would look like this. So on the first channel, I just want to send an integer and then whatever. On the second channel, I want to send a bool and then do whatever. Now I've got to worry about two continuation channels. And since I'm in this resource passing style, I need to return two of those continuations. And you can imagine if you have 3 and 4, then this gets a bit of a mess. So you essentially have to return all these continuations in a data structure. You can, in this example, I don't really return a result from the calculation, so you would have to pair that as well. Of course, you could say, hey, I can encapsulate that in a monad. This works nicely, but it works only nicely for a single channel. And there's work like, for example, Pucella and Toff, where they did some embeddings in Haskell, and it gets pretty crazy if you look that up for multiple channels. Now, what can we do? So what we are suggesting is that we are introducing a split primitive for session types, which is very similar to what you would do in a borrowing style. And the idea is, if you have a channel type like this, send two integers and then close, then with using a notion of borrowing, which we implement here as a split primitive, you can split it into a borrowed prefix that says, hey, send an integer and then return. And then this gets composed with the remainder, the continuation channel as we had it before. Now, so essentially the split primitive looks like this. If I have a function, if I have a channel type that is composed of a borrowed prefix, that's something ending with return, and then a continuation, then split can split it into the borrowed prefix and this continuation type. And this is not just any pair here, but this is a left to right ordered pair, which prescribes that you have to consume first the borrowed prefix and then the continuation, because otherwise you would be breaking the protocol. And we'll come back to that in a few minutes if we have them. So what are we going to do instead? So we are proposing to replace this resource passing API by a borrowing style API. Yeah, so now the sending takes instead says, oh, I want to have a single shot channel where I can just send an alpha and then return. So we are only dealing with borrows that just do a single communication. Similar for receive, we're saying, hey, the channels should allow first to receive an alpha and then return. Yeah? So whatever the rest is, that's dealt with by the splitting. And now the types get less messy, I would say, less involved than here. And also the code, well, you can argue about that. In my examples, I'm using sending. Trust me, if I would use receives, then the code here would be much bigger. So here you can already see this typical order reversal that you have when composing functions. So here I have to first I'm sending the last. So in the code, it looks like I'm first sending 4 and then sending 17, but of course, due to function composition, it's really the other way around. Here, this is sort of looks like an imperative style. So here you can see I'm using the borrow notation in order to grab the first prefix here of the channel, send 17, send 4. And here you can see that this really nicely scales if we have more than one channel. So both of them are represented by borrows, int return, send a bool return, and then I can just use these channels in any order whatsoever. And you can see here already some benefits of that. And we claim that this is a more modular style because you get rid of this resource passing. You are not forced into a particular programming style. You don't need to waste polymorphism on something that doesn't need it. You can use it for more interesting things. And it's also much, much easier to return values. I mean, here it's always unit because I'm just sending stuff. But you have a slot there where you can return something and it doesn't get cluttered with having to return resources. Let's talk a little bit about ordering. What I promised you before. Suppose we have a channel of this style, first send an integer, then send a bool. And now let's take a borrow of that channel, right? So let's take the first communication plus return, let's take that as a borrow. So now, after doing that, our context looks like this. We have x bound to send int and then return, semicolon, c bound to send bool and then close. And the semicolon will turn out to be the important thing. Namely, if I now try to extend the program by sending true on C, we get a type error because the semicolon advocates that the binding for X must be consumed before the binding for C. Yeah, so the binding for C is not available at that point. So what you have to do first, we first have to act on X. So then this binding for X is consumed by the send. Afterwards, it's gone, and we can further on consume the binding for C. Now, what's the secret sauce behind the semicolon? That's called BI context. So we're using BI context and ordered and unordered composition there. So here we have the semicolon, that's ordered composition, and it means stuff that is bound in the left gamma has to be consumed completely before stuff that's bound in the right gamma. Whereas the normal one, which I'm writing here as with this parallel symbol, that's just the normal composition for linear bindings, and you can reorder them in any way that you like. Now, this is the story. We had a similar story last year already in a paper about type state. So this is good enough for the sequential part. But now we have the session types. We have to worry about concurrency too, right? I mean, that's the point of having session types. So let's have a look at a very small program where we want to try to do borrowing across threads. Now, so again, we have a protocol that has two interactions so that it fits on the slide. But now we're doing a first borrow that happens from this channel that happens inside of a fork. And we're doing a second one that happens in the continuation. Now, how do we enforce that things actually happen in the proper order, right? I mean, the type system has to make some decision. Maybe it's naive and says, this one is the string borrow, is the int borrow, which would fit with the typing, and this one is the string borrow. But we have no way of enforcing that, right? So the execution of the two threads here, that can happen in any order. So what do? Well, we change the representation of borrowed channels so that the splitting that happens in the moment we take a borrow, that attaches some sort of synchronization to the ends of the borrowed channel. So essentially what happens is if we are finished with the borrowed channel, then we are actually handing off ownership of the underlying primitive channel to the next guy down the line. Yeah, so essentially when we're doing this, this receive here, in addition, we are dropping the channel and passing on the underlying communication, primitive communication channel to this next receive. So how does that happen? That happens in our paper by performing a transformation, or in a compiler that would do the transformation. So essentially what we're doing is we're representing a borrowed channel by a pair of cells. So, and the first cell here is really one end of a one-shot channel, and on this one-shot channel we are expecting to receive the primitive channel on which we do the actual communication. That's maybe a bit, let me show it to you in a picture. So that's the typical representation of such a borrowed channel. So here, what color is that? Yellow or whatever, orange. So this part is the port, the cell on which I expect to receive the primitive channel from the left, from a borrow, for example. And so when I want to do any action on this guy here, I have to wait so that I get the primitive channel from the left. Then I can do whatever I want. Usually I do just some primitive operations on them. And when I'm done with that, I have to hand off the primitive channel to my continuation. Yeah? So I always push it back into this blue part, which means when I take a new borrow, yeah, so when I say, so this here stands for R, when I split this further up, all I have to do is, like here, I have to insert a new cell so that when I'm finished here, I'm not pushing directly to this guy here, but I'm pushing to this intermediate cell, and then this subsidiary continuation can pick it up, and once that is done, it passes it on to the final part, to the final continuation. And I'm not going, due to time reasons, I'm not going to show you the translation, so there is a nice picture in the paper that also serves as the proof of the type preservation of this translation. So what do you find in the paper? So we are presenting a type system for session types with borrowing. As you have seen, heard, this is based on our version of ordered types. The way we implement it is we are doing a type preserving translation to a version of GV with priorities. And the reason why we do that is this translation yields type soundness, so we don't have a separate type soundness proof. And it also yields deadlock freedom, because the system priority GV is guarantees deadlock freedom. The nice part about that is our translation that introduces all these intermediate cells and extra communication doesn't introduce any deadlocks, despite even if we do it in a strongly sequential part. So moreover, we have a mechanically verified artifact in ACTA, and we have an implementation with practical extensions, and you can find all that in the artifact. And that's what I wanted to say. Thank you.
I think we have time for one question.
Thanks, Peter. It seems like nice work. I'm still a bit confused. In the example you gave where you forked off this thread, how does the type system know to do the splitting? I mean, how does it know that the forked thread goes first?
Good question. So the type system just makes an assumption about that. So it would just split it according to the occurrences in the text, and then this mechanism, the synchronization mechanism, kicks in and makes sure that this actually gets enforced at runtime.
Okay, so it's just left to right in the text.
In this case, it's sure. In this case, it's just left to right. Yeah.
Okay. Thanks.
Yep. Good.